Okay, so in chapter 2, what we were studying was electromagnetic radiation mainly, the photons. And what we have seen was, although electromagnetic radiation, we are used to describing it as a wave, we saw that it has particle-like properties. It has an energy. The particles making the electromagnetic radiation has energies given proportional to their frequency. Now, how do we know that? Well, basically, we need to make this, we are led to this conclusion by two observations. One was the Planck's law of blackbody radiation, and the second was that we had the photoelectric effect, which told us that these photons, whatever they are, they transfer their energy completely to the electrons. You see, we had made an estimate that if you have some light falling on a metal, for an atom to acquire enough energy to eject one atom, you need many seconds. But observation told us that at the instant the light falls on the metal, the photoelectrons are emitted. There is no such accumulation, and that can only be if the electromagnetic wave contains packages, compact packages that can deposit all their energy in a given atom. So we know that they have energy given by h nu, and they are moving at the speed of light. That tells us that their masses is zero, but if their masses is zero, then their momentum was E over c, or no, E over, E over c. This was their momentum. We know their energy is h times nu. And what is c over lambda? Wavelength. So the momenta of these photons is h over lambda. So we have this system. I mean, we are used to looking at it as a wave. Then we saw that it has a particle properties. Now we can look at the same system, in fact, as a particle, but it has wave-like properties. It makes interference, for example. So if you know the energy of this particle, the photon, so we can determine its frequency, dividing by this constant. So we know its frequency. If we know its momentum, we can determine its wavelength by just dividing h, that same constant, by this momentum. But why should photon be special? We have all kinds of other particles. Like the electron is a particle. The proton is a particle. I mean, you can just think of many particles. So if photon is not special among other particles, then these wave properties should also be seen by all the other particles. It was de Broglie, well, it was his PhD thesis. He defined the de Broglie wavelength to be h over p. And since we know the momentum of an object with mass, this should be h over gamma m times v. So if you, in a sense, well, what he did is he just exchanged these two quantities, if you like. But it should have many significant influences on how we interpret nature. You see, if it's a wave, we should be able to see interference patterns. Well, let me search for electron interference. Now, we will discuss it in more detail, but let's see if I can show you the video now. Anyway.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there.
This is the double slit experiment with electrons instead of light.
Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biboson, thus creating a uniform distribution without any interference when accumulated. Under such conditions do electrons form a uniform distribution. But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible. Clearly visible.
So these are with the electrons, not with ordinary waves we know. And, well, you see the fringes, so they interfere. You see, the first case would be, okay, there is this slit, so the electrons will probably hit one of the sides, so they will go either this way or that way, not necessarily perpendicular, straight, but it doesn't explain these dark spots. It should be more or less Gaussianly distributed if we don't have interference. But now the question is, interference of what? What are these waves? So we are used to thinking of electrons as very small spherical particles with a very small radius, but at least this experiment, we also had previous experiments, do show that they are also waves. Now we have in fact, we can just borrow what we did using light. You see, when we were discussing light, we said that, okay, there is this, on one hand we have the wave picture, where we have these two double slits, and the waves are diffracted in each one of those slits, and if you just pick up a point on the screen, there will be two waves reaching there. So if they interfere constructively, if they have the same sign, at that point they will add up, so there will be a large electric field, you will have a non-zero light intensity. If they are subtracted, if they have opposite signs, then we would see destructive interference and we will see dark lines. And when we said that, okay, electromagnetic radiation itself is made up of particles, and if you remember, we had identified E squared is the probability. Now, when we identify the electromagnetic wave as made up of a collection of particles that we call photons, and then the intensity was proportional to the number of photons that falls in a given point on the screen. So if there are fringes, if there are dark regions on the screen, it just means that no photon went there. If we have bright spots, it means that many photons went there. The same interference pattern can be explained using this quantity. And then we said that, okay, on one picture, the intensity is the electric field. In the particle picture, the E squared is not the intensity itself, but E squared is the probability that a photon goes to a given point. But now we will do the same thing for the electron case. We will say that these waves are probability waves. Now, this will be an important concept for us. Just like in the case of the electromagnetic radiation, we identify the magnitude of the electric field squared as the probability. Here we will also define a wave. It will have some value. this value at the point r at the time t, and then we will say that psi of r t absolute value squared is the probability. Let me put the word density here to observe the particle at the point r at the time t.
How do you define psi for electron? The function psi. How do you define it for electron?
Now we will study it. We will study how we can describe, how we can write down this function. We will look at it.
Probability dediğiniz aslında time average değil miydi? Vektör olarak gösterdiniz ya. Ben onu düşünüyorum.
Where? Here.
Magnetop is.
Well, the electromagnetic radiation is described by the electric field, which is a vector.
Pointing vektörler geliyor diye hatırlıyorum. Onda time average'ını alıyorum.
Pointing vector is the flow of energy. But you see, here what we do in the double slit experiment, Young's double slit experiment, so we have these double slits. On the screen we have these interference fringes, and here the intensity is proportional to the electric field vector squared, the magnitude squared. Now, in the case of the electron, we don't define a vector. It's just some number. Well, not exactly a number, but for the time being, let's say we will just treat it as if it's just a number. But the concept is important over here. Now, we will be describing about the probability. Well, psi is usually called the probability amplitude. Probability amplitude. Just like the electric field is the amplitude. As a wave, it has an amplitude. Its squared is our probability. Here we have psi squared is our probability, and psi itself is just the amplitude at a given point r and t. The probability cannot be negative. Well, that's not a problem because we are already dealing with the absolute square. This is definitely a positive quantity, whereas the amplitude itself can be both positive and negative. So if the probability, the total probability amplitude is the sum of two different amplitudes, then if they are both positive or both negative at a given point, they will just enhance each other. If one of them is positive, the other one is negative, they will de-enhance each other. They will just make each one smaller in magnitude. So that is how we can still observe the interference pattern.
Why both absolute value and square? Why not only square doesn't suffice?
Well, nothing tells us that it should be real. It doesn't have to be a real number. That's kind of the problem. Well, not a problem, but you see, even in electromagnetism, next year you will study the electromagnetism in more detail, you will see that we usually prefer to describe electromagnetic waves as complex quantities. And then when we need to compare it to something physically observable, we take the real imaginary part or the absolute value. So here we are kind of leaving it quite general. The wave function can be complex, can be real, but we don't know for the time being. Nothing tells us that the probability amplitude or the wave function nothing tells us that it should be real number. Of course, if eventually there is a principle that tells us that it should be a real number, then by using the absolute squared, we are not really making a mistake. If it turns out to be real, then it is the absolute square is just the ordinary square of it. So for example, if you know the wave function of a particle, and if you have a very small volume, delta V, then this psi of r of t squared times delta V, this is the probability. Well, if we are sure that the particle is somewhere, then this should be 1. If you just sum over all such very small volumes, making our universe, this should be 1, because the particle is somewhere. This is called the normalization of the wave function. Well, let's see, what else can we say about this wave? You see, we haven't yet discussed it. We don't really know it. But once we say that it should be a wave, secondly, since we see the interference phenomena, if there are two waves reaching a point at a given time, then the total wave at that point is just the sum. This is called the superposition. This is necessary to explain the interference phenomena. Well, we know that any kind of wave can be written in terms of harmonic waves, because we observe interference. Otherwise, we wouldn't observe interference. Of course, within the limits, you see, you might add a very small nonlinearity here. It might be so small that it doesn't disturb the fact that we see interference patterns. Then we have the limits. Up to now, at least, the measurements didn't show us that there is a non-zero, nonlinear term here. Linear approximation turns out to be enough. And since we know that, at least for the time being, we know that this wave satisfies the superposition principle, we can write any wave in terms of harmonics, sines or cosines.
And by the way, that we showed that those terms are in reality not linear, but it's an approximation. Is that correct?
Well, you see, all the laws that we say are correct. They are just approximations. That's the best we know. So we don't know if this is wrong. We don't know if there is another term there. But what we also don't know that whether such a term is absent or not. Current experimental limits tells us that there is no such term. That's the only thing we know. Maybe, I don't know, in the next 10 years we will find out that we should add some more terms there. That we don't know. It's not completely eliminated. We only have limits. Well, you see, with gravity, you can have very sophisticated things. Okay, so what is this K? It's the wave vector. You can write it in terms of other properties like 2 pi over lambda. And, well, lambda is, if you like, h over p, or this is p over h over 2 pi, which is usually defined as p over h bar. That's the definition. And omega is the frequency. It's nu over 2 pi, no, 2 pi nu.
2 pi times nu.
2 pi over t, or 2 pi nu, or 2 pi e over h, or e over h bar, whichever one you prefer. What is the velocity of this wave?
Sağda e over h bar squared yazdım.
Where? What's the velocity of this wave? Omega over k. Well, omega was e over h bar. K is p over h bar. So this is e over p, which is c squared over, well, let's say this is the phase velocity, c squared over v. Because v is just v over c squared is just p over e. Do you see a problem? Well, you see, what do we know? We already know that the wave, whatever wave it is, it should satisfy the superposition principle. I know that every wave I can write in terms of the harmonic waves, just as their superposition. Since I can use the superposition, whatever my wave is, I can always write it as sum of such terms. So if I know the general properties of these terms, I might be able to say something about this wave. That's why I'm studying harmonic waves. And this is basically our first obstacle of this harmonic wave description. You see, we define the phase velocity, but then the phase velocity of this wave turned out to be c squared over v. V is the speed of my particle. You see, if you are trying to describe a particle, let's say the electron. The electron moves with a speed v. But it just turns out that this wave that I'm trying to describe my particle is moving faster than my object. Even faster than the speed of light. So you see, we know that v is less than c. So c squared over v is definitely larger than c. This wasn't a problem in the case of the photons, because for photons, v is equal to c, so the phase velocity is c, which is the speed of the photons. But now we have a problem. It just doesn't work. But as your friend had curiously asked, why use harmonic waves? I mean, this mainly tells us that harmonic waves are not so physical. So what do we do? Well, usually we just add the waves to create a particle or to create an actual wave. And, well, one problem over here is how do you define the speed of a wave? You see, in the case of the harmonic waves, you just look at some peak. It will be moving with this speed, another peak. All the peaks are moving at the same speed. All the troughs are moving at the same speed. This is what we call the phase velocity. Now, this is not a realistic wave, because this wave goes up to infinity in both directions, and it exists from t is equal to minus infinity, and it should exist up to t is equal to plus infinity. But no wave is like this. The waves, all the waves we can create will have some finite length. But we can create such finite waves by just adding various different wavelengths. So let's just look at this case. We have, let's assume that psi has this form. If you just sum these waves, what you will get will be cosine kx minus omega t multiplied by cosine delta k x minus delta omega t, where this k is defined as their average, omega is the average frequency, delta k is k1 minus k2, and delta omega is omega 1 minus omega 2. Now let's look at what these things are. Can you read it? Well, this is just how it will look like at a given time t. Let me just increase the time. Let me slow it a bit. Well, at least here you see that how it moves. The speed is kind of easy to identify. Well, let me make it a bit even longer. So they're just shifting to one side. Now let's add two waves, not just one. And the other one will differ from this one slightly.
Are they multiplied?
Hmm?
Are they multiplied?
No, they are added. So they differ by dk in wave vector and by dw by their frequency. Let me give them some numbers. This is, let's say, 0.2. This is 0.1. Well, to see it better, let me just increase the x range. So if you already, you have the amplitude is large, it gets smaller. The amplitude increases, it gets smaller. Here we have what's called a package. So it's a quite localized energy distribution is over here. So here, this will actually describe a train of packages. So here we have one package, here we have the other package, we just see half of it. Here we would have the third package, fourth package, etc. So this is an infinite train of energy packages. Now let's see how this changes as a function of time. You see, let's just follow the separation between two packages. This is how they move. This is how fast it would move. Now let's try to follow one of the peaks. You see, this is one peak. It now came to the interface. Now that peak is over here. You see, the peaks are moving faster than the packages themselves. You see, what we call a particle is just an energy package. A localized object, most of the time it's localized, at least let's say, an energy package localized in a given small volume. So these packages is what we call the particles. You see, this phase velocity is not really important for us. What is important for us is the velocity of these packages. It should match my particle. You see, if my particle is over here at a given instant, and if it is moving with some velocity v, its probability distribution should also be moving with a velocity v. Because otherwise, me saying that my particle is here moving with a velocity v will not make any meaning. Even if it has a meaning now, it basically means that I have some finite probability in this region. Well, at the next region, that finite probability had already moved faster than the speed of light. That means my particle is not moving with a velocity v. So the probability wave itself should be moving with my particle. Only in that case, I have a sensible definition of the velocity of the particle. So let's see what is this velocity of the packages. Well, you see, this wave that I wrote over here, I cannot use it to describe a single particle. It describes a train of particles. I have infinitely many particles, just one after the other one. Here there is one moving in that direction. Here there is another one moving past in the same direction. And then that already went out. This particle is moving towards the right. Now it reached the right of the screen. So each of these packages is one particle. Now let's calculate their velocity. What is the velocity of each one?
So the particles are not yani aslında düşündüğümüz gibi birbirinden ayrı ve bağımsız şeyler değil.
You see, here I'm just using very simple wave functions. This wave function cannot be used to describe a single particle. That's what I'm saying. Later on, if what I understand as a particle should have a wave that should look something like this. This is one particle. I can use this to describe one particle. It's somewhere over here. And this whole thing can be should be moving to one direction with the velocity of my particle. Then the question is, okay, you see, here we were looking at the harmonic waves to describe my particle. One problem that we faced when we were using harmonic waves was that these harmonic waves are moving faster than the speed of light. It just doesn't make any sense. And then we said, okay, our new interpretation, let's say, is that fine. I'm not really interested in what's called the phase velocity, but I'm interested in what is called the group velocity. If you look at this wave, well, you see, that second term is also changing very slowly, both with time and with position. And if I would just draw that second term, second factor, it looks something like this. And let me also plot minus that factor. This is what's called the envelope. You see, the product is always less than this one, because the product is multiplied by this cosine whose absolute value is less than 1. So my wave function is always within these bounds. So my full wave function is this one. No. This is my wave function. Well, what is phase velocity? Phase velocity is basically the speed of these peaks. The phase velocity of this wave, you can identify it as omega over k. Whereas the group velocity is delta omega by delta k. It's the velocity of the envelope of my particle. So here what I say is, here there is a particle. This wave can be used to describe one particle over here, another particle over here, another particle over there. Now, what is the velocity of this group velocity? Well, let's see. The group velocity is delta W by delta K, or delta nu by delta P, just divide or multiply by suitable 2 pi's, or, no, sorry, this is delta E by delta P. Delta E by delta P, just multiply by factors of h bar. Well, what is the energy of a particle? This we can also write as delta E over delta V times or divided by 1 over delta P times delta V. What is E? Well, E was 1 over square root of 1 minus V squared over C squared, M times gamma, M times C squared. So dE by dV is, let's see, minus 1/2 minus 2V over C squared, gamma cubed, MC squared, or dE by dV is V over C squared, gamma cubed, MC squared. Or sorry, maybe even there is a shorter way. Let's say E was equal to square root of m squared c to the 4 minus p squared c squared. Okay, this is shorter. So forget these. The group velocity is the derivative of energy with respect to momentum, which is equal to minus 2p c squared divided by square root of m squared c to the 4 minus p squared c squared. No, this is plus, sorry. This is 2p. Now there's a 2 over here from the square root. These 2's cancel. So I have pc squared over e. But this is nothing but the velocity of my particle. So what we did, on one hand, the first thing we did was seeing the interference pattern for electrons. And well, historically, we did that experiment using crystals, like the X-ray diffraction. We had observed electron diffraction through crystals. We know that the electrons should be described by waves. But if they are described by waves, so on one hand we have the particle, on the other hand we have this wave. Well, the photons already taught us a lot. So since we know that the electromagnetic wave, we should also interpret it as in terms of photons, particles. It taught us about this concept of the probability of having a particle at somewhere. So we are just borrowing the same terminology. But now these electron waves, let's say, have mass, unlike the photon. So, okay, we are trying to kind of come up with a description, a common description for both the photon and the electron, but there are also some differences, like the mass of the electron. Will that cause any problem? So first we said, okay, let's use harmonic waves to describe the electron. But when we used the harmonic waves to describe the electron, we had this problem. That interpretation doesn't seem to hold because these harmonic waves have a speed much faster than my particle. So if I am used to having this concept of my particle over here at some, you see, we also have to explain Newtonian observations or any observation we did without using quantum mechanics. And those observations told us that if I throw a chalk, let's say, from here, well, I can still describe it as a probability if I like, with the probability of having this chalk at this instant, at this point is 1. It is 0 everywhere else. And I can say that there is this probability also should be moving with the chalk. Because as I'm throwing the chalk, let's say at a later time, the chalk is over here. That also means that the probability of observing the chalk here is now 1. And everywhere else is 0. So this probability wave should be moving with my chalk. But this harmonic wave does not move with my chalk. Then we said, okay, that's not really a big deal, because actual waves cannot be such harmonic waves, because these harmonic waves, basically, they extend to infinity. So they describe such a probability that this probability is the same everywhere throughout the universe. Because this wave is the same here, here, there, in the next galaxy, etc. So if I know that my chalk is over here, I should have a wave which is non-zero only in this region and negligible everywhere else. Even for the electrons, I know that I'm sending the electrons. I have an idea about where this electron is at every moment. At least they are in my experimental setup. They are not at infinity. That I'm sure of. But that means that my wave describing the probability of the electron cannot be harmonic. Harmonics just extend to infinity. But then if I don't have the harmonics, the concept of the velocity of a wave itself is kind of problematic. Because the velocity in mechanics we define using some points. But the wave is an extended object. How do you define the velocity of a wave? There are various definitions of the velocity of the wave. Two commonly used ones are, one, the phase velocity. The second one is the group velocity. And the idea in the group velocity is that even if you just sum, let's say, you don't know k definitely, but you know that there is an experimental error bar of your k. So your wave is made up of just the superposition of those waves, having k values very close to each other. In this example, it was k1, k2, and omega 1, omega 2. I was assuming that they are very close to each other. So if that is the case, when I sum those two waves, I get this one. So this is what's called the beats. So if you think of these as a sound wave, you see, look at this one. The sound is very low over here. It has a very high, there's a very high sound over here. So you will see this beating sound. Anybody who was playing any instrument?
When you tune strings very close to each other, they beat.
Yeah, that's ideal. That's one way of, in fact, adjusting the strings, the tension of the strings.
Böyle bir hareket yapmakla olasılık fonksiyonunu birlikte taşımak arasında ne fark var?
What do you mean? Okay, let me just first correct that one. The electron is not moving like this. The electron is just moving, just like the photon is not moving like this. The photon is going straight.
Böyle hareket etmesiyle, hareketinin olmasıyla, wave function'ını hareket ederken birlikte taşıması arasındaki fark nedir?
Well, let's see. You mean this one or the previous one? Nothing, that's what we had shown. If we have these beats, we have more than one wave, the group velocity is actually the velocity of the particle. So these groups are moving with my particle, not the phases, not each one of the harmonics, but the groups, they are moving with my particle. So this concept So when we are talking about particles, let's say, we say that, okay, the particle is over here. Let's say you say that the particle is somewhere over here, right? So what you actually mean is that you see that particle over here, or the probability distribution for this particle looks something like this. Now, if this particle is moving with a velocity v, after some time, you would expect your particle to be somewhere over here. So the probability wave should have moved with the particle, and now it should be over there. This is what we would expect. And in fact, this is what happens. This is not a harmonic wave. Since this is not a harmonic wave, the fact that the harmonic de Broglie wave is moving faster than the speed of light, we don't really care. If we can make such a wave by superposing more than one harmonics, then we can get such a wave, and this wave will move with the speed of my particle, because this object as a whole moves with not with the phase velocity but with the group velocity. So that is kind of saves us. That is what saves us. Now the problem with the definition of the velocity of the wave is that you see this wave will not conserve its shape. If it looks like this initially, it won't look like that later on, but what it will look like more like this. Now we will see why it happened. It will be broadened, but more or less it's moving with the particle. That's what's important for us. Now the problem with defining the velocity of this wave is, should we define the velocity of the peak as the velocity of the wave? Or should we define the velocity of, I don't know, this point as the velocity of wave because this point moves slower, or this point moves faster? Well, you see, you probably heard about the superluminal travel. So sometimes people come up with, especially in popular science magazines, that I'm not even mentioning the Turkish newspapers. They say that, okay, scientists had managed to send signals faster than the speed of light. Or there was this claim that the signal exited the medium before it was sent in. Well, they are true, by the way. They are true. I'm not going to say that the experiments are wrong. What I'm going to say that the interpretation is wrong. You see, you can define infinitely many speeds for a wave, in fact. What they call the speed is not the speed with which you transfer energy or with which you transfer information. So, no problem. Yes, there were many questions which I stopped. Okay.
The probability, and since we define probability with probability amplitude squared, but how do we define a probability amplitude for a particle? Like you said it can be negative, it can be positive. They can amplify each other if they're both negative. But how come?
How do we describe?
Probability amplitude is formed, or is that is even a physical thing, or should be considered?
Now, you see, let's remember your 109 course. What did you do in 109? The first material, the first topics. No, come on. Schwarz. You see, when you were studying 109, the first thing you discussed was kinematics. That was the description of motion. Then you studied the dynamics. Why does the motion arise? How does it change with time, etc.? So that is what we are actually doing over here. First, we are trying to find about describing our kinematics. Then we will talk about the dynamics. How does these things change with time? Let's do a problem. Okay, this was your reading assignment, but anyway. Particle in a box. So let's say that you have a box and you put a particle inside. What are the possible waves for this particle? Let's say it's one-dimensional, it's closed, it's always inside, it cannot go out. So let's say this is the x-axis. So let's say this is x is equal to 0, this is x is equal to L. Well, the particle is definitely inside. This is u is equal to 0. So basically, I am looking for a wave function whose energy is less than 0, the total energy. Well, we already know that the solutions should be either, let's look for a harmonic solution. It won't be a real problem here, because this doesn't extend to infinity. Even what we claim to be harmonic will not really be a harmonic. So let's say that, let's look for a function sine kx or cosine kx at t is equal to 0. Well, you see, there is this potential energy. It's at rest. So that already defines me a reference frame. I'm in the reference frame in which this potential doesn't change with time. No, you see, I already chose one potential. You see, just let's look at a different potential, the potential created by one charge. You see, okay, if the charge is at rest relative to me, the potential will be just like something like this, right? If it's a negative charge. This is the potential energy, potential. Now, if in a different reference frame, that potential is now time dependent because it's moving. But here I'm saying that my potential is at rest. There is no motion of my potential. So I'm fixing my reference frame. This is the reference frame in which this potential is at rest. This one? No, I'm just imagining some potential. You see, this room, you see, we are now inside this room, right? Why can't you go out through the wall? No, I'm not doing any tunneling yet. I mean, classically, why can't you go out of the wall? There are forces. If I try to cross the ceiling or the wall, let's say, there will be forcing pushing me. And if the wall is infinitely strong, well, the stronger I push, the stronger the force will become. So the force can actually exert infinite force to me. Well, I can say that there is a potential corresponding to this force. And that potential can exert an infinite force to me. That means the derivative of that potential is infinite. So that's just a step up. So it's this potential. You see, what is this particle doing? Mechanically, classically. There's no Newtonian mechanics. Just classically, what is this particle doing? No, there's no force acting on it. When it hits this wall, there's an infinite force acting on it, and it bounces back. When it hits here, there's an infinite force acting on it, so it bounces back again. So it will be bouncing back and forth. So this room is actually such a potential well for us. This is a three-dimensional potential well. And, well, this is just a one-dimensional potential well. Well, a more realistic description would be, for this room at least, it is this one. There is some potential in the wall. Outside, the potential is the same as our potential energy inside will be the same as the potential energy outside. So if we try to get in through the wall, again, the wall will exert an infinite force to us. So this is actually describing us, in a sense.
Yani ben bir olasılık fonksiyonu taşıyorsam benim her daim dışarıda oluyor.
Why? How do you know that? How do you know that your wave function extends to outside?
Hiçbir zaman sıfır olduğunu
Why not? You see, we don't have node dynamics. We haven't yet discussed the dynamics. The dynamics will answer whether the wave function outside will be 0 or not. Here we are just making a very simple description. A non-relativistic system even. So the energy, if we call this height, you see this is minus u0. The energy of the system is, we are just calling it p squared over 2m minus u0. A very, very simple system. And if we were to assign some wave to it, we can assign a sine wave or a cosine wave to it. There's no time because I'm not looking at the dynamics. You can say that this is at a given time, at a fixed time. Which time? I don't know. At t equal to 0 if you like. Well, let's see. We are inside, right? Inside this classroom. None of you is outside. Do you agree? Well, half of you is outside, but you're all inside. So the wave function here should be 0. Here it should also be 0. Well, let's say, what about this point? Well, in physics, we like things that are continuous. Eventually, we will see why the wave function has to be continuous. It's not just a desire. It has to be continuous. But for the time being, let's just stick with continuous functions. Well, at x is equal to 0, on this wall, on one side it is 0, so it should be 0 on the other side. So it eliminates the cosine. I cannot have a cosine wave function. So it has to be a sine. Secondly, I know that here my wave function has to be also 0, because just on the other side of that wall it is 0, so just on this side it should also be 0. But that tells me that sine k times L should be 0, or k times L has to be equal to an integer multiple of pi, which tells me that k should be equal to an integer multiple of pi over L. Well, the kinetic energy of this particle is p squared over 2m. And note that n can be 1, 2, etc. This is h bar squared k squared over 2m. This is h bar squared pi squared over 2m L squared times n squared. This is the kinetic energy of my particle inside the box. Well, you say n cannot be 0, which basically tells us that the kinetic energy of this particle can never be 0. If you confine a particle in a finite box, it definitely moves, because of the wave property. It just cannot be at rest. Secondly, it just cannot have any energy. You see, there is this number over here, which is determined by the mass of the object, the size of the box, and these constants. The kinetic energy of this particle in a box can only be either equal to that constant, or 4 times that constant, or 9 times that constant, or 16 times that constant, but it cannot be, let's say, 10 times that constant. It's not allowed because of the wave property of this particle. Well, you see, cosine cannot be because it's not continuous. You see, at x is equal to 0, on one side it is 0, so on the other side it also has to be 0. So cosine is 1, it's definitely non-zero. Any last questions? Well, we will discuss that. I mean, ask that question when we study dynamics. At least for the time being, we haven't discussed anything about how this wave actually changes with time. But what we expect is that the wave should be moving with the particle. That is what we wanted to know, wanted to make sure. And the group velocity is fine. So as long as I'm not talking about harmonic waves, the wave will be moving with my particle. Now, how does this wave change with time? That is dynamics. That is something else, something we will discuss towards the end. Okay, see you on Thursday.